and skills also go into fabricating these transistors. These transistors have to be fabricated very precisely, and it's a very capital intensive industry. We need uh, tools and maintenance that run into billions of dollars. It's very expensive. You have to have millions and billions of these transistors in a very tiny area. They have to be very precisely designed and fabricated. And so the techniques and the tools that are used to make them also have to be very sophisticated, because you're going to make transistors that are nanometers in dimension. They not only have to be precise, but you have to repeat them millions of times. So it's crazy. I mean, 100 or 200 years back, this would seem like magic. It's so much advanced technology today. So, but this in general, the silicon transistor is what is being shrunk to such small dimension, and this is because our processors, our chips in our cell phones and our laptops, they're becoming smaller and becoming more faster and more efficient. So that's the domain of silicon. But today I'm not going to talk about silicon transistors, because this faculty development program is about also future roadmap and challenges. So we'll talk about this different kind of transistors which are increasingly becoming important in our daily life. We may not even realize it. For instance, a car is becoming more electronic and electrical and less mechanical, if you see. So wherever there is some electronic component, transistors are inevitable, correct? So today I'm going to talk about gallium nitride. It's the second most common semiconductor in the world now, after silicon. The reason is because all the LEDs that we see in the streets, in your homes, garages, everywhere, these LED bulbs are actually made of, the active light emitting diode is made of gallium nitride. And LED is a very large industry that runs into tens of billions of dollars. And because of this wide scale proliferation of LED, gallium nitride is a second most common semiconductor we see around today. And this, had gotten Nobel Prize about 8 years back, and LED is a very mature technology. I'm not going to talk about the optical side of gallium nitride today, but gallium nitride also has fascinating properties for electronics and, for power and RF electronics, which is where I'll try to talk about in this presentation. So what is wide bandgap? And the title I made, this is a wide bandgap semiconductor. All of you know what bandgap semiconductor is. So this material has a bandgap which is large. How large? By wide bandgap, we typically mean bandgap larger than 3 electron volts, for instance. Silicon has a bandgap of approximately 1 electron volts, which it's pretty large. Okay? So this image, on the y-axis, it shows the bandgap, and then the x-axis, it shows something called lattice parameter, which is like the distance between 2 neighboring atoms. So, it's typically plotted in this way. So gallium nitride families are here actually. So aluminum nitride, indium nitride, they are the sister compounds, and together at gallium nitride, they form the nitride family. And you can alloy them. You can make gallium, indium nitride, gallium, aluminum nitride. You can alloy and make this wonderful material whose properties can be tuned or tailored to our needs. You can do the engineering of this band diagram to make very interesting and new kinds of devices that can really perform much better than silicon. These materials are all direct bandgap. You can see that going from infrared to deep ultraviolet, the entire visible spectrum is also encompassed by this material. So you can make photodetectors and LEDs of different wavelengths like UV, blue, green, etc. And this is a very important optoelectronic application of this. Now, wide bandgap material also includes some other semiconductors like gallium oxide, diamond, silicon carbide. They have their own pros and cons. I'm not going to talk about that. Gallium oxide is very emerging. It's new. Diamond has been around for some time. It is actually theoretically much better than gallium nitride, but the problem is the material, to grow the material in a larger diameter is very difficult. And unless you can grow in larger diameter, you cannot make a viable technology. That's the problem. Silicon carbide is also a very mature technology now. It's for high power electronics, and it's very important for kilovolt class of devices. So those are also other wide bandgap devices, but I'm not going to talk about that so much. So this slide might look a little busy and a little bit scary. So let's not worry so much. I just want to highlight the fact that gallium nitride, with respect to silicon, has much more advantages in terms of some fundamental material properties, say breakdown field. So breakdown field tells you at what electric field strength the material can break down electrically. You can see that the breakdown field of gallium nitride is roughly 10 times that of silicon, which means for a given material dimension, gallium nitride can block 10 times higher voltage than silicon, which naturally means that for having high voltage, high power kind of devices, gallium nitride can perform better than silicon in principle. Okay. Similarly, you can see that mobility is very high, electron velocity is quite high, you can get very high charge, and all this enables gallium nitride devices which can carry higher current and still block higher voltages than silicon. Makes it very, very attractive for high power switching, high frequency radio wave device, radio frequency devices, and so on. And because this is a very wide bandgap material, you can go to much higher temperature and still be okay. For instance, if you take a silicon MOSFET, you cannot operate it at very high temperature, like say 500 degrees Celsius or 800 degrees Celsius. It will not work because it will go become intrinsic. All of you know it, right? At high temperatures, silicon will lose its semiconducting property, but gallium nitride will not. People have actually experimentally shown that gallium nitride transistor works fine even at 1000 degrees Celsius, which is impossible with silicon. So for high temperature electronics, for radiation, hardness, for very hazardous environment, gallium nitride devices can be much more robust and can withstand this hostile kind of temperature and situations than silicon. So these make it very interesting actually. Now coming to the first segment, power electronics. Power electronics is a very fast increasing area of electronics. So as a country develops, the fraction of the total energy that we use in the form of electricity increases. So long back, we used to do cooking in firewood, then gas stove. Now in many advanced countries, it's electric cooking. So we move towards electricity. So petrol and diesel are used for vehicles. Now it's getting electricity. There are some explosions and burnings of electric vehicles, two-wheelers. We are hearing in the news, but that's more to do with reliability or maybe battery and other issues. The companies have to look into that. That's a different issue. But in general, we are moving towards electric vehicles, electric two-wheelers. So the fraction of electricity, fraction of energy we use as electricity increases. In another 10 years, we will be having more electricity rather than non-electricity based energy. Okay, that's how we move towards a greener future and etc. etc. Now, whenever there is electricity, you have to convert them from one form to another. It is inevitable. Your laptop, for instance, works at around 20 volt DC approximately, but the plug point that you have at home is around 220 to 240 volt AC. You have to convert that AC to DC and also step it down from 240 to just 20 volts. Similarly, your cell phone, you need to step it down from 220 volt to 5 volt AC to DC. So this energy conversion from DC to AC, AC to DC, and higher to lower, lower to higher is inevitable, it's unavoidable. We have to do it. Power grids will supply at kilovolt on the lines, and then you have to step it down and things like that. Or you convert the power, manipulate, shape, tailor the power is about power electronics. And power electronics is a very important component because more and more things around us are becoming electronic and electrical, right? When the LED bulb has this, the heat sink and the adapter, you have to convert that AC to DC. So even solar cells, right? So whether it is charging of electric two-wheelers or vehicles, power conversion is becoming more critical, and power electronic devices are becoming the backbone of this power conversion. And of course, it's not to say that silicon devices cannot do it. Silicon devices also can do this power conversion. The transistors, they can enter not so much options. So if you touch the laptop adapter, it is warm because it is not efficient. It is dissipating heat. Now, modern day on adapters that are tiny, that are temporary. In very few years' time, the laptop adapter will be inside the laptop, very, very tiny, like a thumbnail. So it's becoming super compact and very efficient. They don't heat up. From silicon to gallium nitride devices. Gallium nitride, by virtue of its material properties, can make devices that are superior to silicon fundamentally, and that's why they enable this. So that is why this gallium nitride and other wide bandgap semiconductors are so interesting, so attractive. So this is what I was talking about. The laptop adapter is already planned. This picture is from pre-pandemic, so it's now even smaller than this. The charges are getting really smaller. Indian market will soon see this. The only problem is they are slightly expensive, but as the volume scales up, the price will come down. It is market economics. There's no reason for that. So this pie chart that I'm showing you actually is maybe several years back from US. It shows that the amount of power energy is so much. Yeah.
Sir, your voice is breaking.
Ma'am?
Sir, your voice
My voice is breaking?
Yes, sir.
Let me remove my earphone maybe. Am I better now?
Yes, sir.
Am I better now?
Yes, sir. Yes.
Okay, sure. So what I was saying is that the amount of energy lost or the power lost in converting from one form to another is actually more than what we can generate from wind and solar. So conversion loss of power is a very significant thing, and that we do not pay attention to, or maybe many of us are not aware of. We only talk about battery storage and solar energy, but when you convert the energies from one form to another, you need to be efficient. Otherwise, there's a lot of overhead, there's a lot of wastage, and with increasing population and energy scarcity, this needs to be addressed. And herein comes the role of gallium nitride and other wide bandgap devices. Okay, so this is another image. For instance, the bottom is an inverter, the top the bottom inverter is made of silicon-based devices. The top one is made of wide bandgap devices. You can see that the size is reduced substantially. The weight has also reduced by about 80%. It has also become more efficient, by the way, as it becomes smaller. Nobody says that, I need a bigger, heavier system. Everyone says lighter, compact, smaller system. So this is where wide bandgap devices are making a change. And I wanted to bring this point to the audience here because this is about a faculty development program on recent trends. So this is where one of the trends are actually in power electronic industries, is that there are more and more companies in the West who are trying to now build gallium nitride devices and prototypes around it that are entering the market. And very soon we'll see them all around us. Even the chargers in vehicles will be based on gallium nitride. They are already starting to, we just don't know it yet. So just to give a little bit more technical depth, power electronic system will have many components, but the semiconductor transistors are primarily used in this topology sector, which consists of switches that can, these active devices that can switch the power on and off. And there will be some components like resistor, capacitors, etc., inductors that can store energy. Okay. So typically in a switch mode power supply, or an SMPS, this is this single pole double throw kind of a concept where essentially you have a mechanical switch that can go from one point to another point. It can make the circuit open and close. So by doing that circuit open and close, you can modulate the amount of voltage that you get at the load. For instance, if you close and open at 50% duty cycle, half the time it's open, half the time it's closed, then the voltage and the output is roughly half that of the input voltage. So you step it down like that, so it's like a buck converter, very, very simple concept. Now, this mechanical switch, of course, will be unstable, and you cannot mechanically switch hundreds of thousands of times per second, kilohertz. Over time, it will break down very easily. It's not also feasible. So you need an electronic switch that can do it with very, comfort and without much difficulty. So you essentially replace that mechanical switch with an electronic transistor and diode or other kind of electronic devices. This is the role of semiconductor devices. You have a transistor and diode, for instance, that will do the exact same role as a mechanical switch is doing. So this transistor and diode combination can basically control the current. It can make it open, it can make it short. That is the beauty of these devices. Silicon devices also do it, and they are used widely. But as I told earlier, they are not very efficient now at higher power and higher switching speeds. That's why we are looking towards these new material and devices. These are not new. I mean, gallium nitride is now there for 20, 30 years. Okay. This is basic transistor description, don't worry. So ideally, when the device is off, it should completely block all voltage. There should be zero leakage current. And when the device is on, there should be no voltage drop. That is the ideal situation. But in reality, a semiconductor device, no semiconductor device is ideal. And that is because even in the most idealistic cases, semiconductor by definition, by the nature of its property, will have some leakage current when it is off. That is because there is a background concentration in the semiconductor, intrinsic carrier concentration, that one cannot get rid of, that one cannot eliminate. As you go lower temperature, you can reduce it, but our normal devices have to work at room temperature, not lower temperature. So there will be a baseline leakage current, there will be a baseline voltage drop that we cannot avoid. The objective of better and better semiconductors like gallium nitride is to make sure that the leakage becomes lower and the on-state voltage drop becomes lower. So you want negligible unnecessary voltage drop when you're switching it on, and you want negligible unnecessary leakage current when you're switching it on. These are the two important conditions. And of course, there is switching speed. So when you switch it on and off, it should abruptly and immediately go from 0 to on to 0 and stuff like that. But in reality, it takes some time, some nanoseconds maybe. to go from on to off. So we also want to minimize the time that it takes. If it takes a lot of time to go from on to stay off, then you cannot switch the device faster, and that will be a problem. So switching speed is also very important, and it depends on so many other things, right? So similarly, a diode ideally should be immediately on and completely closed, but in reality, there is a turn on. All of you know diode turns on at 0.7. It should turn on as low as possible, and then the leakage breakdown should be very high, but in general, it breaks down in some voltage, right? Similarly with transistor. Okay? So the very important thing in a power transistor as a switch in all this application, it has to act as a switch, is that the breakdown voltage should be large and the on resistance should be low, so that the voltage drop is low. Okay. However, there is a fundamental physical limit. It's called Baliga figure of merit. It was proposed by an Indian professor called Jayant Baliga at US in North Carolina State. I think it's North Carolina State University, I guess. So he came up with this idea that, not idea, it's a fundamental physical law that by nature of the very nature, the semiconductors will have a limit, which means you cannot get infinitely better breakdown voltage for a given on resistance, or for a given breakdown voltage, you cannot arbitrarily reduce the on resistance, which means in very simple term, if you want it to be high voltage device, your on current will have to come down. And if you want it to be very high current, your breakdown voltage has to be sacrificed. So you need to sacrifice between two quantities. To get one, you have to sacrifice other. I tell my students, it's like life. In life also, we need to sacrifice something to get something. You cannot get typically best of two things at the same time. So it's very similar in electronics also. You have to sacrifice one to get something else. Okay. Now this Baliga figure of merit is a constant for a constant material. So for silicon, it is certain value. For gallium nitride, is a certain value. So what happens is that in gallium nitride, this Baliga figure of merit, because it depends on critical electric field, it depends on mobility, which are superior in gallium nitride than silicon. What it means is that the Baliga figure of merit for gallium nitride is much better than silicon. What it means is that for the same on current in gallium nitride, you can get much higher breakdown voltage than silicon. So this is a great advantage. Now, all this discussion about gallium nitride is actually for a gallium nitride transistor. It's called high electron mobility transistor. And the structure is shown here. So if you have a layer of gallium nitride on top of which you put a thin layer of an alloy called aluminum gallium nitride, then by nature of their properties, at the interface, you have something called 2DEG, which stands for two-dimensional electron gas. It is a very high density of electrons, almost like a metal, but not exactly metal, but it is confined in the Z direction. So in the XY direction, it can move, but in the Z direction, it cannot move. It's like confined. It's like a quantum well. So that's why it's called two-dimensional. It's not three-dimensional. It cannot move in the Z direction. And if you make proper electrical contact, so between source and drain, you are able to push current. You can connect the source and drain. Electrically, they will conduct. It's a transistor. And you can put a gate that can control the density of this electron below the gate to turn the channel on and off. Okay. So this is in principle the very basic of a gallium nitride transistor. It's called high electron mobility transistor because the mobility is fairly high. Okay. Now, gallium nitride, this is a unit cell picture of a gallium nitride crystal. So the yellow ones are nitrogen atoms, the gray ones are gallium atoms. They are bonded in like a hexagonal kind of a geometry, but it is not a pure hexagon. It is a slightly distorted hexagon. It's called Wurtzite. And the way they are bonded, this gallium and nitrogen both are kind of a polar elements in a way that the bond that they form is polar. So the electron cloud is asymmetrically distributed between the gallium and nitrogen. That is reason number one. Reason number two is that there is a electronegativity difference between the two atoms, gallium and nitrogen. The electronegativity difference. And number three, that this is a distorted hexagon, which means it is not ideally a hexagon, it's Wurtzite. There's a distortion of the bond length, the structure. Because of these three reasons that I told, this material is polar. What it means is that there is a dipole that forms across this unit cell. It's like a sheet negative charge on the top, sheet positive charge at the bottom. Even without doing anything, there will be this. So this polarization that forms is very unique. It is not there in silicon. It is not there in gallium arsenide or gallium oxide or other semiconductor. In very special category of semiconductors, only this is there. So gallium nitride is one of such semiconductor where there is an inbuilt polarization without us doing anything about it. And This is called spontaneous polarization. And this spontaneous polarization gives an electric field inside the crystal. Now that electric field can be exploited and used to our advantage to make devices that can really give very new performance or very better performance, superior performance. So this unique ability to engineer polarization is a very unique feature of gallium nitride. It's not there in silicon. Okay. So basically what it means is that if you stack these unit cells, millions and billions in number to make a layer. So each unit cell is, for instance, half a nanometer. Okay. So if you have millions and billions of these unit cells, you will have few hundred nanometer, maybe a few micron. So that layer will have a sheet of negative and positive charge at top and bottom respectively. That is a very beautiful thing. You see that we can make transistors even without doping because of this property. So if you take a piece of aluminum gallium nitride and put it on top of gallium nitride, so there will be strain in aluminum gallium nitride because their latest constant of material properties are not the same. So because of the strain, there will be another component called piece. I don't know, this recording is starting and stopping. It's kind of interrupting here. I don't know. Every 2 minutes I get this message that recording is stop, recording is starting. Anyways, that's fine. So this aluminum gallium nitride layer is strained. And because of this strain, there's an additional polarization called piezoelectric polarization. All of you know piezoelectric effect. So because of strain, there's an additional voltage drop in a way, you can say. So when you put this aluminum gallium nitride in contact with gallium nitride, there's a huge net positive polarization at the interface. And so that gives rise to a band diagram like this. There's a wider band gap aluminum gallium nitride, there's a smaller band gap gallium nitride. Gallium nitride is also wide, but aluminum gallium nitride is even far wider. So that's why the band diagram looks like this. Now there are two a sheet positive and negative charge at the interface, so the bands will bend. Why? Because there's an electric field. And because of the electric field, the band diagram eventually looks like this. And at this interface, there is a two-dimensional electron gas that forms. It's very high density of carriers, as I told you. And this is unique to this structure because you can get it without any doping also. It's a very, very interesting property that without doping, you're able to get a 2D electron gas. Now, just give me a second. I'll drink water and come. Sorry. So now the problem with gallium nitride, however, with all these beautiful things, there are also challenges. Otherwise, everything would be gallium nitride today. It will be eventually, but there are some problems. The problem one is that gallium nitride large area wafer, single crystal wafer is very expensive. It is not possible to grow. This is a gallium nitride wafer. You can see in the image. It's a 2-inch wafer. It's transparent, of course. It's a wider than that. It's a 2-inch wafer is very expensive, maybe $1,000, $2,000. Compare that with silicon, where 6-inch, a much bigger wafer is probably $10. So if you want to compete with silicon, only the performance advantage will not be enough. You need to also bring the cost down to make it competitive. If your price of a 2-inch wafer is $1,000 versus price of a 6-inch silicon wafer is $10, then it is impossible to compete with silicon on cost and scalability issue. Now, making large area gallium nitride wafer, as I told you, is prohibitively expensive. It's also technically almost very, very difficult, probably impossible to make 6-inch, 8-inch. There's material issues. It's not the same material as silicon. You cannot do bulk growth. All these issues are coming up. So the solution is to grow gallium nitride on a different substrate. However, when you try to grow it on a different substrate, then the substrate on which you are growing is different from gallium nitride. So there will be mismatch issues. And those issues can lead to material defects because you're forcing material gallium nitride to grow on a foreign material, which is not like gallium nitride. So there will be some issues at the interface, some defects will propagate, we call them dislocation, and this is inevitable. And those will reduce the performance of the device. So typically people grow on silicon carbide. It's very expensive also, but it's very good substrate. You can use it. And people in defense industry space where cost does not matter, they use silicon carbide to grow gallium nitride. Very good devices are formed. Sapphire is very cheap like silicon, but the problem is sapphire cannot withstand heat. And these transistors are for high voltage, high power, so heat is there. So sapphire is not good because it cannot handle the heat. Silicon is better in managing heat, and you can grow gallium nitride on silicon. However, silicon It's a very different kind of material, and growing is very, very challenging. It's very challenging. The defects and dislocations of gallium nitride on silicon is a recurring problem, and that leads to reliability issues, performance issues in gallium nitride devices. But then if you grow on GaN on silicon, then you can beat the cost, or you can come very close to the cost, because you can make it scalable. You can make large area. You can have. So these images, this slide is from Professor Vasu, who is our department chair. I collaborate with him. So, if you do not grow gallium nitride properly on silicon or any other substrate, it can lead to delamination like this, cracks in the film, a very large, grain boundaries and uneven surfaces, huge density of dislocation, which are missing lines, or deep pits that will form. So these are nightmares for material scientists, and it takes years and years for material scientists to at least try to solve some of these problems, so that the growing layers are of good quality, on which you can make good quality devices. Otherwise, there is no point. If your material is so bad, then all the advantages that gallium nitride could give you in principle, it will not give you, because the material is very bad. So the material has to be of decent quality, right? So this image again is from Professor Vasu. You can see that this is gallium nitride film, and on this is silicon. So you can see these white lines are missing line of atoms called dislocation, and they are defects. Their density is decreasing towards the top on which you are going to make the device. The density is worse at the bottom in case when you are starting the growth. Now, this reduction in the density or the white line is not magical, but there is a lot of material engineering that goes into these layers, managing the stress by using superlatives, grading, etc., which will enable you to reduce these defects as you propagate upwards. Okay, so that you cannot completely eliminate them, but you reduce them so that the device will see fewer number of dislocations. Okay, now this is the basic structure of a gallium nitride transistor. I told you there's an aluminum gallium nitride layer on top of gallium nitride, where you have a very high density of 2D electron gas that you use for high electromobility transistor, that is used for all this power switching application. Now, this gallium nitride layer has to be grown on, for instance, silicon. And I told you there are missing line of atoms that give rise to all kinds of leakage paths. The background in gallium nitride also has a lot of impurities. That is because of the nature of the growth. That lead to some kind of leakage path. We need to reduce the contact resistance. Sometimes the gate leakage has to be reduced. So there are so many issues to be solved and addressed that are being increasing. There are so many aspects to it. Some people are trying to improve the contact resistance. Some groups are trying to reduce the impurity in the gallium nitride buffer so that more and more voltage can be blocked. Some groups in industry or academia, they're trying to reduce the dislocations here so that less and less number of fewer number of dislocations and defects can propagate. And some people try to remove the silicon substrate completely after growing, so that the silicon, because the silicon breaks down when the field reaches the silicon, so you can improve the breakdown voltage. So there are n number of approaches to improve the device, to improve the material, engineer the stack, engineer the device, and so on and so forth. Okay, we at ISC also have been doing a lot of these activities ourselves. But there are also groups in the US, Europe, Japan, who have been doing a lot of work for many years to make this a mature and viable technology. And now gallium nitride transistors are commercially available. They are used in laptop chargers in the more modern and advanced versions. And increasingly, the automobile industry will be using these gallium nitride transistors for their electric vehicle charging. So this is a technology that is already there. It's not only for textbook. It's not only for academic research. Okay, just keeping that in mind. So just to again reiterate the basic operation of a device, because we're talking at a very high level, talking about all these, advantages, disadvantages, scalability, but at the very physics, at the very fundamental level, you see whenever the device has 2D electron gas below the gate, we call it on. It's always on. That's why it's a normally on device, because if you do not apply any voltage to the gate, it is an on channel, which means you have to apply a negative voltage on the gate to make it off. You have to do something to the gate to turn it off. That's why it's called a normally on device. And these devices are useful, but normally off devices are more useful, like where you have to do something to the gate to turn it on. It is always off. So those kind of devices are more, because if suddenly the gate terminal becomes floating, then this device will carry current, which is a safety issue. But people have been working around that in any case. So whenever you apply negative voltage on the gate, you can basically deplete the channel below the gate and you can turn it off. So when you turn the channel off, then the spacing between this gate and drain will decide or will determine how much voltage you are going to block, because the spacing between this, is the voltage that you're going to block depends on the field in between these two regions and also the spacing between these two regions. So as you keep applying more and more reverse bias, you're basically depleting 2D electron gas towards the drain, and eventually the limit of the spacing will decide how much voltage you can block. Now you can say that I can increase the spacing between gate and drain so that I can block more voltage. Yeah, sure. But then if you increase the gate and drain spacing, then your on resistance will increase, which means your on current will decrease, because if you make a resistor longer, it becomes more resistive, right? So that's why it's a trade-off. It's a sacrifice between the breakdown voltage and the on current also. So what people have shown, this is not from our group, this is a literature from Japan. So if you increase the spacing between gate and drain, you can keep increasing the voltage that you're blocking until the field will penetrate and reach silicon. So once it reaches silicon, silicon will break down. That's why after certain spacing, the voltage does not increase. So this is y-axis is breakdown voltage, x-axis is the spacing between the gate. You can see that after certain time, the voltage does not increase. That's because your vertically it has broken down, because silicon is rich. So then you have to make these layers very thick. If you make these layers very thick, then you can minimize the chances of the field reaching silicon at the same voltage. So you have to not only make this device design carefully, but also the material has to be grown thicker to be able to block higher voltages. Now the problem is, the thicker you grow the material, more problems come on. There could be possibility of cracking, for instance, because these layers are grown under stress. So there is always an interplay and always a trade-off between this material growth, between the devices and performance. It's not very easy. That's why it needs a lot of time, a lot of years of study actually. So these are some of the devices that we had made at ISC some years back, just to show that this is a scanning electron microscope image of a device, a gallium nitride transistor. This is source, this is drain, and this is gate. There's a gate finger here. It's a small area device. The gate finger is probably 1/10 of that of a millimeter. This is the periphery here, and it can carry current of few hundred milliamps per mm. So that's low current only. And this is the leakage that shows, it's up to 50 volt. We have much higher breakdown voltages, of course. You can block certain voltages. However, to actually make power electronic circuit, you need larger devices so that they can carry very high current, like 5 ampere, 10 ampere, 20 ampere, 30 ampere. Those are very, very current. And for that, you need large devices. So what you see here is a very large device. If you zoom in, then this yellow winding circular kind of things are actually gate finger. So there's a gate between source and a drain. So this is source, drain, source, drain, source. So it will continue source drain for maybe 50 times or 100 times, so that the gate that is coming back and forth, it will wind up back and forth. Eventually the gate will be like very large, like 100 micron, a millimeter, or 50 millimeter, 200 millimeters. So large width of the gate will enable you to carry larger current. So we have also done that. This is a full 2-inch wafer fabricated at ISC at SENS, for instance. We are able to get up to 5 amps. This was actually long back. We have been able to get 10-15 amps of current also. And we are able to block on these large devices, we can block 100 to 200 volt. But on smaller devices, we can block up to 600 to 700 volts. So the idea is now to make 600, 700 volt devices that can carry very high current. For that, there has to be packaging, there has to be heat sink. There are so many things. It's not just the transistor that we fabricate. You have to make the metals very thick so that they can carry very high current. You have to package the device and put a heat sink so that the heat dissipation is taken care of. Because if you have 10, 20 amps of current, your breakdown voltage is 600, 700 volt, and the amount of power you will dissipate is very high. So you cannot just put it on a wafer and put it on a probe station. It will burn. There will be arcing of voltage. You need to put a heat sink. You need to have a package. So those are other work and activities that need a lot of effort and time and study. Just making the transistor is not sufficient. Characterization is a different ballgame. So here I'm showing you that this device was able to go to 5 amps. It's a not very, very big device, but fairly big device. And we were able to get an on-off ratio of 10⁴, 10⁵. Leakage was in hundreds of microamp, which is very good. And this is many generations of transistors were made. So this was one of the earlier generation. This is one of the more recent generation. Large area device. This is, for instance, gate. This is drain. This is source. So many fingers are being fed by source and drain with gate. So multiple layers of lithography and fabrication are needed. It's not an easy process. It takes several years, and many students and project staff and postdocs develop the process. It is a very, very resource and time consuming task actually. We're able to show that Even after packaging or dicing the device, the leakage characteristics were not changed, which means that devices are fairly good. And these were packaged. This is many years back, maybe 5-6 years back. We were able to package the device 5 amps 40-volt devices. We call them Eigenfact 40, and these were the first power electronic devices indigenously made in India in gallium nitride. These were also tested for DC-DC conversion at 2 megahertz by CDEC Trivandrum. That's the Government of India lab that also makes this power electronic circuits. Then, while we are doing these circuits, we also work on fundamental research aspects, and many other groups also work, but I'm not saying we are the only one, but we try to study how dislocation or how the defects affect the performance. If a device fails, how will this dislocation affect, the role that they play, the different layers play to manage the stress, to manage the dislocation, versus how the devices are performing, how the leakage is performing, the mobility, the on current, and how we can relate those to the fundamental material properties. All these things need to be studied. So our students, we do a lot of these activities and these studies also at SENS ISC, trying to find out the reliability aspects, some of it, the on current leakage and the relation with the material property, for instance, because we grow on silicon, so material is always an issue. But commercially, gallium nitride devices for power switching are all on silicon. So this is, all the industry is also very much interested in a lot of this work. So this is very obvious. I have talked to people in the industry who say that they're very interested in the kind of work that we are doing, because it basically tries to address some of the concerns that industry has in gallium nitride and silicon devices. Okay. So that was on power electronics. There's a lot more activities on that, but I'll put a stop here, and I'll spend the next maybe 10 minutes or so, 15 minutes on discussing about another aspect of gallium nitride transistors. So one segment is the power electronics. I told you about switching the power, charging, adapters, and all this power conversion. Another very large and very interesting and very important area of electronics is RF, or radio frequency microwave electronics, where gallium nitride transistors are being increasingly used for amplifying signals at the gigahertz range. So this is not a switch only. This is not a switch per se, which is to supply power or something, modulate the power. This is about amplifying the signal at gigahertz frequency. Okay? Amplifying the signal and sending it off. So you can make power amplifiers based on these transistors, and this is very critical. This is very important. Why? Because so many industries and so many segments use it. So all your cell phones have a power amplifier, because you have to amplify the signal and send it to the nearest base station. All the Instagram posts, all the voices that you're talking about, everything has to go as 1 gigahertz, 0.9 gigahertz, 1.2 gigahertz electromagnetic wave to the nearest base station. The power amplifier in your cell phone is made of indium phosphide or indium gallium arsenide based material, which are also compound semiconductors, not silicon, because they can give you better efficiency, power handling, and other etc. properties compared to silicon. However, the base station, the tower, the cell phone tower needs to take the signal, it needs to amplify, it needs to operate at higher power, maybe couple of hundred watt of power, RF power it has to generate. And there comes the importance of gallium nitride. So gallium nitride transistors are now being increasingly used by the cell phone towers like Huawei, Nokia, Ericsson. They use gallium nitride power amplifiers now, because they can give you better efficiency and better output power at this 1 to 2 gigahertz range, for instance, for base station, cell phone base station infrastructure. As I told you, it needs a few hundred watt, for instance. Similarly, satellite communication, and especially spaceborne communication and radar. Military radar depends heavily on gallium nitride, because you can scan the enemy skies to a greater depth. So if you use silicon transistor based radar, then your output power will be low, so you can scan only a little bit. If you use gallium nitride based radar, your power is so high that you can scan much more in the enemy sky. So gallium nitride, the word gallium nitride itself is in ITAR restriction. What it means is that in USA, gallium nitride is one of the top 10 or top 20 most sensitive items of product or research or whatever. Okay. Part of the reason why I get a US visa only for 1 year, they do a background check, they did not give me visa for 1 year because I work on gallium nitride. It's a very, very, very sensitive material for defense, because it is used to make radar that can scan the enemy skies, and only a few countries can do it. So US or any other country, no country wants no other country to take the technology. Even Europe and US, even England, UK and US, they don't have this. They are very close, but they don't have this sharing policy in gallium nitride. You see, they have their own programs because they cannot share. It's so sensitive. So gallium nitride based radars are very important, and India, we are trying to develop that, and there's a lot of interest, the encouragement from government of India also. So hopefully in a few years we'll get more gallium nitride based transistor radar. But this picture here basically shows output power on the y-axis and frequency on the x-axis. So you can see that gallium nitride is for delivering higher power at higher frequencies. At smaller power, smaller frequencies, silicon, gallium arsenide, they do well. The cost is also low. So gallium nitride may not be a competitor at low power, low frequency. There's a lot of application for that, cell phone, for instance. But base station, radar, satellite communication, these might benefit, these are benefiting a lot from gallium nitride. Okay. So again, the basic material property of gallium nitride, which is its ability to switch in high temperature, its high mobility, high charge, high voltage operation, all these enable transistors that are more efficient, low noise, rugged, smaller size, and can give higher output power. That makes gallium nitride devices very attractive for microwave power amplifiers also. Now, 5G is, we hear all the time 5G, 5G, 5G. Different companies have different standards. Maybe in India, there has not been a rollout of 5G yet, but it will soon be sometime. And some countries are already rolling out. So there are different frequency bands that are identified. I think in India, it will be sub 6 gigahertz, 3.6 gigahertz or so. That will be the frequency for 5G. In some countries, it will be 26, 28 gigahertz and so on. So you need very high data rates. You need very low latency and super high speed, data rate that you need. And this transistors that can give good output power at very high efficiency and are really fast. So here, this is an image from a company called Qorvo. This is a gallium arsenide, gallium phosphide based transistor that can give you, say, 650 milliwatt, okay, of power. This is a gallium nitride transistor that can give you 2,800 milliwatt of power. So you are able to get 4 to 5 times higher power. The size has become probably 6 or 7 times lower. So that's crazy, and it's also, by the way, much higher, more efficient. So it's crazy. I mean, that kind of compactness in size, how with the increase in power, is incredible, right? That's the benefit of gallium nitride. So at this high frequency, especially like 20, 28 gigahertz and so on, gallium nitride can give you much better efficiency and output power. And so people are looking at it more seriously now, for the civilian application, apart from radar and space, of course. So the thing, gallium nitride is primarily grown on silicon carbide for this microwave application, because these are high cost applications like military radar, satellite communication, even cell phone base stations. The cost is an issue, but not so much. You need performance. And that's why gallium nitride is grown on silicon carbide. Unlike in power switching, e-vehicle charging, laptop adapter, where GaN is grown on silicon, because you have to compete with consumers market, a consumer electronics market. Now, gallium nitride for radio frequency application is also being increasingly looked for GaN on silicon, because you can reduce the price significantly. You can scale it up. So, for instance, if you want to put gallium nitride in cell phone, then the price has to come down. Cell phone amplifier. So that's why gallium nitride on silicon is now being actively looked into. And so, because of scalability and manufacturability issues and integrability with existing CMOS fabs. So there's a lot of activities at ISC. Also, we are embarking on this work of gallium nitride on silicon platform, where we try to make these devices on silicon. But there are different kinds of problems to address at gigahertz. We don't need 600 volt blocking. We probably need 50 volt blocking or 60 volt. However, it has to operate at gigahertz instead of a kilohertz, for instance. So there are differences between the high power power electronics and high frequency power electronics. I mean, this is a high frequency power delivery. Okay, so there is all these things. So in radio frequency application, we don't need to block 600 volts. So leakage can be high. We don't care so much about the leakage. We do care, but not so much about the leakage as much as in the 600 volt power device. Of course, there the leakage has to be really low. Here we can sacrifice the leakage a little bit. However, we cannot be compromising on the loss, the RF loss. So whenever there's an RF signal, there can be capacitive coupling to the substrate. So you might lose some RF power, radio frequency power. And so these defects and dislocation, the way we grow these layers, how much the RF loss is happening, all these need to be characterized very well. We need to understand this very well so that we can make a platform which is really it gives you really low loss on RF. Okay. So that's very important. Now, so there are different things. One is the loss that has to be minimized. One is the strain that has to be also minimized, because you do not want a lot of bending and bowing in the layers. Contact resistance has to be also minimized, much better than in power electronics. In 600-volt devices, contact resistance can be a little bad, not a problem. But in RF devices, microwave devices, the contact resistance has to be super duper good, so that's very important. And one of the most important aspect is that your surface has to be protected by something like a silicon nitride, because the defects and traps on the surface can lead to something called current collapse. When the current collapses, then you will not get any RF power. So that's an issue here. So this image is taken from Dr. Hari Chandrasekhar's paper that was published a few years back on the different mechanisms that lead to loss. About different, for instance, nitrogen might diffuse. There may be hydrogen from the growth. There may be oxygen diffusion. All this might lead to RF or microwave loss, dislocations, stresses. So many factors are there which can lead to RF loss. So one has to really understand the interface, the material growth, so that all this out diffusion and in diffusion of these different species like carbon, hydrogen, oxygen, nitrogen, this has to be minimized. How can you grow the layer very insulating with lower and lower dislocation density, and etc. These are very important aspects of the thing. So I'll not go into much details of this. So people in the industry also have been working a lot, and along with academia, on fixing these issues so that you can grow gallium nitride on silicon for microwave power amplification purposes. Okay. So now people have been even showing circuits and amplifiers at very high frequencies like 40 gigahertz, even 100 gigahertz. But reliability of these devices are yet to be investigated, and the performance of these devices on silicon are not as much as gallium nitride on silicon carbide, where there is cost, but the performance is also superior. So at IISc sense, I'll skip this maybe, we are working a lot on a special type of gallium nitride transistor on silicon. It does not have an aluminum gallium nitride, but it has an indium aluminum nitride barrier. We're not the first group or the only group. There are many groups that have worked on this. There are many groups that have reported excellent results even before we started. So I'm not claiming we're the pioneers here, but we have been working significantly on making this very scale devices with very short gate lengths, scaled down version, so that we can get microwave performance. So this is a scanning electron microscope image of such a device. This and this are essentially the source. This is the drain, and this is the gate. You can see this is the gate finger. It's probably less than 100 nanometer in gate length. That is very, very small for radio frequency devices. We should not compare it to silicon CMOS, 10 nanometer, 5 nanometer. Those are not for RF. Exactly, they are for logic and power processing, processors. But for RF power, 100 nanometer gate length is actually very small. We even gone up to 40, 50 nanometer gate length. So these are scale devices for high frequency applications. So these are some characteristics. We are getting very high current, up to 2 amp per millimeter, for instance. We are doing a lot of studies on terms of something called short channel effect. So if you change the gate length, how is the control of the gate on the channel? That becomes poorer and poorer as you bring the channels closer and shorter and shorter. It's called short channel effect that all of you know. We have studied that for this special kind of transistor. We are able to get cutoff frequencies approaching 90, 100 gigahertz. This is before de-embedding. This is before taking out all the parasitic components. It is around 90, 100 gigahertz. And, this is one of the highest values before, de-embedding. And after de-embedding, that means after taking out the parasitic effect, the actual transistor cutoff frequency is close to 200 gigahertz. This is probably the third or fourth highest value in the literature in the world. We are not the highest, but we will be there soon. I mean, this is a very scale device, 40 nanometer gate. We are working on improving the contact resistance and the other parameters, but you can see that this is the chart for the cutoff frequency versus gate length, cutoff frequency, gate length product actually. So we are one of the highest values, but we still have some, more to go. But we started only 2-3 years back. So in that small time with pandemic, of course, we are able to come very fast. So we hope to be there, another year or so, we should be able to do that. So now to kind of summarize everything in perspective, the two segments, one is power electronics, one is RF electronics. And there are many, many things in each of them. I can talk offline, I can discuss in details in another chat session or something. Here, I'll just try to summarize the. If you want to charge an electric vehicle, you have this onboard charger where you'll have this converter. The converter has a lot of circuit assemblies, passives and other things, but a key part is a package transistor. The transistor package looks like this, package transistor, and a bare transistor on a die looks like this. which comes from a wafer on which you dice the device. And the wafer, to get this transistor, you need to follow maybe 7 or 8 or maybe 10 layers of lithographic techniques of layers. Each layer will have probably 10 steps. So you might have to follow some 70, 80 steps inside a clean room to get this particular transistor over a week or 2 weeks time. It's very complicated. Okay, it's not easy. And similarly, for wireless communication, for radar, you need this high power radio frequency or microwave devices that can amplify power at gigahertz, several gigahertz, which also, these are all images from Sense, by the way, not this and this is the internet, but these devices and systems, and these are all images that our group people have taken, fabricated. And we are able to grow gallium nitride on silicon thanks to Professor Vasu, who is the chairperson. His group has been developing this ability to grow GaN on silicon for the last 10, 12 years. And now it has reached a stage where we are able to grow gallium nitride on silicon very well. And some of our earlier students who are also guest speakers at this faculty development program, Dr. Anisha, Dr. Shashwat, they have graduated from our department. They are doing very well abroad in Europe and US. They were some of the early people in our department who pioneered and developed this gallium nitride on silicon technology. They had done a lot of work on how to make the gallium nitride on silicon, how to make devices on gallium nitride on silicon. So we are always thankful to them. They have done very good, and now they're doing even better abroad and all. So we need more people. We need more motivated, people to actually address many challenges, come forward, spread the words that we always look for very talented. Not talent. Talent is secondary. Hard work and motivation is primary. People who can actually put in this work towards making gallium nitride a more successful device technology, successful material technology. And we welcome people to visit us, to see our facilities, to encourage students, undergrad, postgraduate, to come work with us. Okay, so that's very important. So in the context of this faculty development program of recent trend challenges, I have to say that gallium nitride technology is starting to grow large. And in the next 5 to 10 years, we will see that many things around us have gallium nitride devices in them. So it's a very right time, and Government of India has already invested quite a chunk of money in enabling a gallium nitride enabling ecosystem at ISC, which will set up a separate dedicated fab line for gallium nitride devices. So that is very important for the country. So we hope that will give rise to more other startups in the country where fabless houses can use these facilities to make the devices. So at ISC, we have faculty members, 7 to 8 faculty members with a cumulative experience of more than 100 years in all aspects of material growth, design, device, packaging system, etc. And we also have a startup that is called Agnit Semiconductor, which is going to make these RF and power devices. But this is my research group from pre-pandemic age, so I have to update the image. Some people have left, graduated, and some people have joined in. But this is from a few years back. So thank you all for your time. This is Center for Nanoscience. I thank all the funding agencies, MHRD, MATI, DST, DRDO, ISRO, among others, funding our center, for enabling us to work, for funding our projects. So thank you everyone for your time. I'll be very glad to take any question if you have any. Thank you.
Thank you, sir. Thank you, sir. I hope all the participants have learned a lot today, and surely you have inspired all of us to pursue further research in this topic. Now, I would like to ask participants to take their questions, and they can post their questions in chat box.
There is a question. It says,
Sir, one of our participants wants to ask that is there any open source software available for testing properties of nanomaterial?
Open source software for, sorry, there was a automated voice that interrupted what you said. What is the question? Automated?
Sir, I repeat, is there any open source software available for testing the properties of nanomaterials?
It does not test the property of material. You need equipments and instruments to test the property of materials, right? You need, if you have a material, if you have a device, you need to put it in some instrument like Raman spectrometer or maybe AFM or X-ray to actually measure. Software will not measure. I hope.
Okay, sir.
Right?
Yes, sir. Yes. Sir, Jain sir wants to ask which devices are preferred for voltage and wideband LNA and power amplifier applications.
At such high frequencies as like V and W band LNA, it is preferably gallium arsenide for low noise application, gallium arsenide and indium phosphide based HEMTs, as well as HBT, heterojunction bipolar transistor, and maybe some MESFETs in some cases. Same for power amplifier, pseudomorphic HEMT, p-HEMT based on gallium arsenide are typically used in real world application like maybe missile seekers, radars, in real application for such high frequencies. So V band is maybe 40 to 75 gigahertz, W band is 75 to 110 gigahertz or something. So at those ranges, gallium arsenide indium phosphide based pseudomorphic HEMTs and HBTs are used in real world applications because they can give very good performance at depth frequency. And the reason is gallium nitride devices are also being reported for such frequencies. A lot of groups in Japan and US are actually doing many W band, LNA and power amplifier work in gallium nitride. But to my knowledge, they are not yet commercially used, or they are not used in real world system because maybe some reliability studies are being going on. But I think very soon, probably in the next 5 years or so, people might start using gallium nitride in W band LNA also in real world application. But I have to mention that these kind of devices are very high end, very sophisticated. You do not get them to buy online or something. It has to be designed around the application. What radar, what satellite, it has to be designed around that. So it's not like off the shelf we can go to an online or some store or buy. It's not like that. But having said that, it's gallium arsenide indium phosphide.
Thank you, sir. So one of our participant wants to know that what is the progress of semiconductor device manufacturing in India?
At the government scale, some DRDO and ISRO labs have semiconductor manufacturing like GATEC in Hyderabad, SSPL in Delhi, even ISRO SCL in Chandigarh, semiconductor complex, which was under ISRO, but now recently it has been moved under Ministry of Information and Electronics Technology, MeitY. So those labs are there, and also SAC Ahmedabad. They also do device manufacturing in limited volume and scale for government and strategic purposes. We do not have a commercial fab like Intel or Samsung so far, but there are academic labs, of course, ISC, IIT Bombay, IIT Kharagpur, Madras, etc., etc. But now the government has released a huge amount of money. I think $10 billion or something to bring together industry and other people to kickstart this initiative so that we will soon have massive semiconductor fabrication ecosystem in the country. So next few years are going to be very exciting, I believe.
Yes, sir. Sir, Ritik Mahakalkar sir wants to know that how can we overcome the semiconductor shortage?
We cannot overcome. Actually, all the countries are fab now. Not only India, many countries, including even Saudi Arabia, who rely on oil. Even Saudi Arabia is setting up semiconductor fab. So because of almost all countries setting up semiconductor fab, the raw material is in short supply. The production is taking long time. Now, companies are not even taking new orders. Some semiconductor part, the company that sells will not even take your order for the next few years because they're overbooked by so many countries. So this shortage of raw material, of equipment, of know-how, it's going to hit us. It's already hitting us. Shipping prices, everything has become double, and shortage has become even more. So all this lithography, for instance, very deep UV lithography, you need a special kind of laser to write those millions of chips, and that laser needs neon gas, which comes from Ukraine. You know how situation is there in Ukraine. So on top of the semiconductor shortage, there's war. So this shortage is going to stay. I mean, it will be very difficult to overcome that. So the shortage we cannot overcome. Hello. Hello, ma'am. Hello, am I audible?
Your voice is breaking, sir.
Okay, hello, can you hear me now? Hello.
Yes, sir. Yes, sir. Yes.
Yeah. Okay. I hope I could answer the questions. Is there any more question?
Yes, sir. Yes, sir. I think there is no more question from our side, sir. Thank you so much, sir. Thank you once again on behalf of International Relation Office and Electronics Department for your valuable guidance. I request you to accept token of appreciation
Yeah, I have it.
on behalf of organizing team and Yashwantrao Chavan College of Engineering for giving us your valuable time. Thank you, sir. Thank you once again.
Thank you very much. Thank you very much again, everyone.
Thank you, sir. Thank you, sir.
Yeah, thank you.
Yes, sir.
1 minute, sir. Please. Hello.
Hello. Left. Participants, you can join. Do not leave. We have to take a group photograph. Kindly keep your cameras on.
Wait a minute, all participants. Okay, thank you all.
Dear participants, kindly join for the next session at 3:30 p.m. today.
All participants are requested to please fill the feedback form. It is mandatory for the attendance.